Good morning, good afternoon, and good evening to everyone who is joining us today. Welcome to block 2 of our webinar series, Strengthening Forest Monitoring System. My name is Patricia Insfran, and I will be your moderator today with my colleagues Marcela Holguin and Ashley Lima. This webinar series is organized by the U.S. Forest Service International Programs and Trade, the Forest Service International Foundation, WILPA Capacity Development, and the Spatial Informatics Group, founded by the U.S. Department of State. Before we get started, a few logistics notes. This webinar is being recorded and will be made available after the session. Simultaneous translation is available in Spanish, French, and Romanian, and we have the channels on the bottom of the Zoom screen, and you can choose your language preference. For questions, please submit your question using the chat and the link that Marcela and Ashley are going to put in the chat question. That is like a board for submit your questions. And then we have two dedicated Q&A space after each session. This is our agenda overview. Today's session focused on forest disturbance monitoring, bringing two interconnected areas, the comparison of deforestation and land use alert systems, and the application of machine learning for fire monitoring upon probability mapping. Also, we will open with a broader look of how forest monitoring technology has evolved over past 15 years. But before we start, we will have Alison Hall to give us an overview. Alison is from the U.S. Forest Service International Program and Trade. Alison is the global coordinator of the SIPA Carbon Program. So, Alison, you can go ahead.
Thank you, Patricia. Welcome, everybody. Thank you for attending our second webinar in this series. Before we dive in, I just wanted to give a little bit of background on the forest monitoring program with the U.S. Forest Service International Programs and Trade. As Patricia mentioned, I'm the global coordinator for the Silver Carbon program. And I wanted to talk just a little bit about some of the context. So Silver Carbon, I think many of you are familiar with, but it was a program that started in 2010. It was an interagency program that was like all things forest monitoring. We worked with USGS, with the EPA, with NASA. And then the last 5 years, prior to last year, we started to focus more on capacity building in tropical and subtropical countries to monitor, measure, and report on forest degradation. We were always funded by the U.S. State Department as well as USAID. But the last year, we kind of shifted away. We're no longer an interagency program. It's just the Forest Service International Programs and Trade, and we are funded by the State Department. But we started a partnership with the Forest Service International Foundation, WILPA, and SIG. And we kind of shifted away from training, and we're working more on building a toolkit. So the last year, we've been developing a universal forest monitoring toolkit as long as guidance and white papers. So this webinar series is kind of coming out of this shift to kind of educate people on the tools that we've been building. This webinar, this is a 3-part series, as Patricia mentioned. The first one was on these broader forest monitoring tools, but today we're going to talk a little bit more about forest disturbance monitoring, alert systems, and then as well as like burn probability mapping, and then their practical applications. So just a little context there. If you have any questions about the forest monitoring work with the U.S. Forest Service, feel free to reach out to me. I'll drop my email in the chat. But with that, I will hand it over to Sylvia. Thank you.
Thanks, Alison, for a very important overview. So we have a fantastic lineup of presenters today. I'm very much looking forward to the conversation. So let's get started. I'm very pleased to introduce our keynote speaker for today, someone whose vision and leadership have been central to building forest monitoring capacity across the globe for over 2 decades. Sylvia Wilson is the founder and chief scientist of Wilpapa Capacity Development. Previously, she managed the USGS Silver Carbon program. Her expertise spans in carbon accounting, capacity development, forest monitoring, remote sensing, greenhouse inventories, and she brings more than 20 years of experience supporting governments and international organizations across Latin America, Africa, and the Southeast Asia. Today, Sylvia will take us through the evolution of forest monitoring capacity development through the regional exchange since 2011, highlighting how technologies and tools and technical expertise and outcomes have changed over time, and the important role of that capacity development has played in supporting and accelerating those changes. Sylvia, the floor is yours.
Thank you, Patricia. Thank you for that kind introduction. Let me check my slides. What view am I on? I need to change views.
Yes, you have the presenter mode.
Okay. All right. Great. Thank you, Patricia, again, and thanks everyone for joining today. As Patricia mentioned, I'm going to present a timeline of a specific model of capacity development from the Silva Carbon country that went on from 2011 to 2025. And I'm focusing this in Latin America, but this model, we ran it through all the regions where the program works: Central Africa, Southeast Asia, and the Pacific Islands as well, and a piece of Central America that is not included here. So this analysis and timeline is based on a specific model where we went to individual countries as we scope the needs that they have for technical capacity to implement monitoring systems. And then we match models with the same needs in the same region, and we develop regional workshops. And in these regional workshops, we brought out experts from all over the world that have solutions or innovations or tools or methods to address these specific needs. And there was a nice avenue for collaboration, South-South collaboration and exchange of ideas and technology as well. And all of those workshops, there were 27 in Latin America since 2011 to 2025. And there was 15 years, 9 host countries, and we separated in 6 distinct technical periods based on this analysis. This analysis was done because all of these exchanges were recorded in websites, and those websites were alive through years. So those websites have reports, discussions, pictures, presentations, and many, many other sets that we use for information to run this. So I mentioned those are the 6 periods. And I'm not sure when I click this link, so I'm not going to click it, but I can share it in the chat. That's the website for these regional workshops, and where all of them are set with again, with pictures, presentations, everything that happened through those workshops. And I know many people in this call has been through this, so you are familiar with what I'm talking about. So we separated in 6 periods and the beginning was really building the foundation. We're talking about like 15 years ago or more when we started the Silva Carbon program. So there were not really monitoring systems in place. Remote sensing data was an issue. We have very little satellite information. So we separate these in 4 areas. Every single period is looking at how data and sensors of constellation of satellites were available at that time, the tools and technology that were available at that time to manipulate that data, the institutional shifts that happened on that period, and the international frameworks also that happened on that period that were kind of key for the implementation of the capacity development. So we start with the period 1, which is the beginning of the program where we have 5 workshops, but it went through 2 years. So in those 2 years, a lot of things happened, right? But in the beginning, we only have like Landsat and MODIS on the data side. And then there was a very basic remote sensing methods. Everything was desktop. And we were talking back then about how to just do a land cover map, right? We were not talking about anything that we're talking these days. It was just very basic. Some of the institutional shifts were that we started with the South-South collaboration among the Andean and Amazonian countries first, and then the international frameworks were, of course, Silva Carbon was conceptualized in 2010, launched in 2011. The UN RED and FCPF begin implementation as well, and GFI was established in 2012. So that was the first period that we pick. And then the second one is more related to carbon, where based on these workshops and the information we have there, we start talking about mapping carbon at that time. So we have more sensors there. Landsat 8 was launched. And we also have radar data back then. This is the period based on the workshops, what the countries were talking about, moving higher tiers of reporting from tier 2 to tier 3. We also start talking a lot about biomass and LiDAR, but not space LiDAR, but like terrestrial LiDAR and airborne LiDAR. And since at that time, we already have developing land cover maps, where accuracy assessment was a big piece of these conversations. Some of the institutional chips was specifically that, moving to a higher tier, and then a big talk about community-based monitoring in the international frameworks that influenced this period, where the GFI methods and guidance, the first guidance was published for RED Plus monitoring. And after that, the evidence from this WhatsApp shows that we start talking about predicting the future. We have more sensors there. We have Sentinel radar, and we have the Sentinel-2 constellation. And at least on Latin America and on this area, we start looking at Brazil and looking at the terror for early warning systems. That's what I mean about predicting the future, looking at what's happening, drivers on deforestation, and risk modeling. One of the key shifts was CPAL and Google Earth Engine. That was kind of like a change on how we do things, and that started in this period and continued through the time that we're analyzing in this presentation. One institutional chips was the capacity development, also was based on the Red Compass, which was an online adaptation of the GFY methods and guidance. International frameworks that happened there was the Paris Agreement adopted, and we have 5 workshops. Through all of those workshops, we pull out all this information from all of the reports. Cloud computer comes next. And on this was We have some workshops in person, we have some workshops online because we hit the pandemic, but we know that for data and sensors, there was a harmonized set of data now with Landsat Sentinel. The JEDI mission started, and we have a lot of workshops on biomass estimation from that, and the NICFI Planet Satellite Data Program also was kind of like a change and a shift on how we did capacity development. Some of the institutional shifts were before that, we were working with specific scientists. We were with a professor from a university, and one of their methodologies was applied in one country. And in these periods, we start looking at whole institutions. We start working with like WRI for the Global Forest Watch, or it shifts how we also brought the capacity to countries as a program. International frameworks and policy, the transparency framework. From that, we start talking about how the Red Plus have to be linked to NDCs and SDGs. So all of that, even though these were technical workshops, all of this technicality training was based on the new frameworks and policy that come up from the COPs and just international frameworks. The next period, it's when we have more integrated national monitoring, and we start looking at how countries were fusion all these data together, optical, radar plus LiDAR, and tools and technologies. That's where a lot of the deforestation alerts that, and I hope this presentation is as a preamble for talks, Paul, as well. The deforestation alerts came to be one of the topics of capacity development. And like I mentioned in the beginning, we didn't do this capacity as an agenda from the program. It was based on needs from countries. So that was one of the topics that the countries really require capacity on, deforestation alerts. And that was, in this period, was GLAD and RAD alerts through the Global Forest Watch as well, but also through Wageningen University and University of Maryland. And then CPAL as well come with the alert. So Paul's gonna present all of that. So now the institutional shifts was also not only monitoring this data, we're talking about alerts, not only monitoring it for, it's not only for monitoring, but also for law enforcement and policy. And there is some evidence that the coming Montreal Global Biodiversity Framework have also some piece of these conversations in these workshops, because they wanted to align, some countries wanted to align some of the targets from this forum as well. And then the last, until we finish with these workshops from the Silva Carbon program, some of those continue through support with Google, but with the Silva Carbon program, 2025 was the last year, and we start talking beyond only forest. That was, well, there's the NISAR launch, but then we have multiple data streams, Landsat, Sentinel, JEDI, radar, all together. In tools and technology here, we start looking at how this technology can be used for also mangroves and blue carbon. So it was a kind of big of a shift, right? Because we start talking about blue carbon and doing mangroves mapping and monitoring workshops. And that was all over the world, but we have some of them in Latin America. Carbon markets was one of them as well. For us, the international chiefs was how one system, that's one question that we have, how one system can support all of these frameworks, biodiversity restoration, carbon markets, so they don't have to repeat or generate new data for each of those reporting frameworks. The international frameworks and policy that were part of the discussion here was the EUDR, the carbon markets, the transition from the biannual reports to the biannual transparency reports as well. Each period also have different questions, and that's very interesting to see how these have evolved in 15 years. We went from like, can we map forests? Actually, can we actually make a map? To now is, can one system support climate, biodiversity, carbon markets, many other things. And so in parallel, we see that around 2011 and around 2025, there is different, like very different, grades. So in 2011, we were only working with Landsat, and now we have multi-sensor, Landsat, Sentinel, Jedi radar, and other data that is coming up, right? We were talking back then about making an annual map that evolved through the years of making a time series analysis, and like through the years, and now we're talking about deforestation alerts and real-time deforestation alerts, sometimes daily. Back then was forest cover, now it's forest cover plus all these things and carbon stocks. Deforestation only was one of the things. And very soon after that, we'll talk about degradation. We're still talking about degradation, deforestation, and restoration. In terms of technology, it was only desktop, GIS. The technology was really behind in comparison to what we're doing now. Google Earth Engine is the cloud, CPAL, all of these things are doing on the cloud now. And then we're doing pixel classification back then, and now time series algorithms. So I can just go on all these parallels and differences, and that shows how much also the landscape of forest monitoring have evolved and changed over time. We pulled out this information based on real workshops that happened, 27 of them through the years and the discussions, but then we can see that nothing is similar from that time to now. And I just want to took another angle on the data side, just to show how things have changed from period 1 to period 6, and how these expanding data constellation have influenced the way countries do their monitoring, right? So from period 1 with Lancet and model, we have like 2 data sets, and period 2 we added, and we have to add 2 with Sentinel-1 and Landsat A, so we have 4. Then in period 3 in 2017, where the countries were working with 5 of them. Then there was the Jedi, so we have 7. And then there was the fusion. We still have 7 data sources, but then there was a fusion among all of them. And then in period 6, we have NISAR, and then we're going to have like biomass and many, many other more, right? But these are the ones that we can pull out from the data on those workshops. Not also the technology and the policy change, also the questions that they were asking back then and through the time have changed. So we start with where is forest? Where is deforestation? How much carbon is there? And as we advance, it's like, why is this deforestation happening? The drivers. Now, can we predict it? Then can we monitor it continuously? Can we support national reporting? And again, that can we generate near real-time alerts from all of that, right? And we are on, can one system support, like, can we, one system that we use the same data can support all these forums: biodiversity, restoration, carbon markets, mangrove, fire, sustainable management. So that's kind of the ideal. One thing that was coming out of this work that Silva Carbon did regionally were the contribution to the GFOI methods and guidance. So those were not just one-off workshops. We have workshops that feed into each other, but also feed into some of the international community of GFOI. So we bring some of this knowledge to the group of the NGD to provide guidance. So the guidance that the GFOI have, and there is many examples, I just put one in there, come also from these exchanges, but the interesting part is that you have a lot of input from the actual end user, which is the countries. Yeah, that's pretty much what I have. That's the timeline. I think that was my 15 minutes. And thank you very much. And now we're going to hear, after that, we're going to hear from one specific topic that was super interesting in the countries. There was the deforestation alerts, because we tried not only in one, we did a comparison between many countries. So that was one of the, like, I guess if I have to pick from all this capacity development, that was one of the highlights, my favorites. But okay, thank you. Thanks, Patricia.
Thanks, Silvia. We are moving to our first session. We will have Paul Berkowitz. Paul is based on, sorry. Can you share your screen, Paul, please? He will talk
Yes.
about deforestation alert system and the comparison. Please welcome to Paul. He has background in GIS and remote sensing. He has worked in various Red Plus projects as scientist, and now works with WILPA capacity development. So, Paul, the floor is yours.
Thank you, Patricia. Can everyone see that? All good?
Yes, we can see.
Awesome. Thank you. Thanks, Patricia. Thanks for introducing this, Sylvia. Sylvia and I put this talk together. We've been doing this for about 5 years, I think. And so just a quick outline, I'm going to give you some context and background on alert systems, an overview of previous workshops, and then the main part is going to be comparison studies from the 4 different workshops. And then I will wrap up with some lessons learned. So I don't really need to cover this because Sylvia covered it. In the last 2 periods that Sylvia covered, we had 4 main priority areas, and alerts was one of them. And that's the only one I'm going to mention today. So we had 4 workshops starting in 2022, one in Vietnam, one in Paraguay, one in Guatemala, and the last one was in Africa in Libreville, Gabon. And they were all deforestation sites. They had deforestation sites nearby for a variety of reasons. And we'll see more about that later. So the workshop goals was to develop a replicable model to assist countries with implementing alerts. And Sylvia mentioned the guidance we produced, which is, I have the link up here on the screen. It's from you can get it off Red Compass. So in terms of the workshops, they all had a similar structure. We started with some background on near real-time monitoring and the benefits. We allowed countries to present the status of their alert systems and their goals. We then had technical experts present various specifications for several different systems. And then the fun part, we went out in the field and looked at these sites, and then we came back into the workshop room, classroom, and we looked at what these systems see from space versus and when they see it. And then you see the comparison side by side of alert pixels here. And so the heart of this talk is going to be comparisons from those 4 workshops. So I'll have a series of maps that I compare and then timelines. So it's basically like 2 slides for each country, and those are probably the 8 most important slides that you will see today, and I'll highlight them later. And then finally, our workshops, we wrapped up with talking about implementation, various guiding principles, how to handle all of the data and work with multiple systems. So just a little background, near real-time monitoring systems or alert systems are algorithms, seems like everything else in the world is an algorithm. They are designed to detect forest or tree cover loss as quickly as possible, ideally in days or weeks, to provide an opportunity for preventive action. And it's distinguished from an early warning system, which identifies preliminary indications of potential forest loss. So those early warnings, they try to predict deforestation, where it's going to occur. Like, for example, near a newly built logging road or road, deforestation is more likely next to that site. Whereas the alert systems, they detect deforestation that's already happened. Alerts are essentially pixels or polygons or coordinates of where tree loss is occurring. And integrated alerts are just a complementary way to visualize more alerts from more than one system. And the last one, lag time, I'm going to show in one more slide. Basically, if you have an event, deforestation event, then there's an observation lag between when that occurs and when a satellite will pass over and see it. There's also lag because once you get that satellite passes over, the data has to come back into a lab or run a bunch of computer routines, process it, make sure everything's okay, and then before it gets sent out to people. So the workflow kind of looks like this. We detect deforestation. There's the analysis and integration, possibly, if there are more than one system. The alerts get distributed on various platforms or by cell phone. And then the end goal is for law enforcement to follow up on actions if there's something illegal happening. So it's a very different purpose than RED Plus, where we're looking for unbiased carbon emissions estimates, and they're after the fact, a year or two later in the performance reports, and the emphasis on accuracy of the emission estimate rather than with alerts. The purpose is to try to stop it before it gets too extensive. So how do these systems work? They mostly have a similar approach. The developers of these systems will define a disturbance, like for instance, the GLAD Landsat system defines 50% canopy loss in a pixel. Then they build some sort of disturbance model or function looking at based on historical values. So we see in the upper right, there's a sepal alert based on SWARE, the shortwave infrared radiation band, and I think it's band 5 in the old Landsat. And this is a little bit old data, but basically we have a harmonic regression in the first period until about 2005, and then there's a giant break in the curve, and that is when a deforestation event occurred. So we're looking, once these models are built, we're looking for changes in the model, big breaks in the curve. And so if you get one point that's anomalous, that is just like a first alert, and we need to confirm it. We don't want to rush out and see what's going on there because it might be an unmasked cloud or something unusual and not a real event. But once we start, like in this curve, we start seeing multiple points, then you can confirm the alert. So that gives you confidence with repeated observations. And then we can fine tune these to minimize false positives. So these are the systems we looked at on the left column. We looked at 3 from the GLAD lab. We looked at RAD from Europe, Tropisco also from Europe. Those are radar based. After the fact, I looked at C-trees for one site. There's a system from Japan, JJ-FAS, Global Forest Watch integrated alerts, which we never were able to test the integrated alerts because one of the sensors was always down. So the Global Forest Watch always collapsed down to a single system like GLAD Landsat because RAD wasn't available. But it is a system with multiple sensors, sepal, and then disturbance index, and then a bulk system, Bayesian updating from Canada. So I shaded some cells here in the first column with sensors. The green shading relies on multiple sensors. Some of them are only single sensor. So the multiple sensors, it's more robust. You're more likely to not have missing data. In the second column or third column sensor type, the blue shading use radar. Not always radar only, but they have some sort of radar built in, which allows them to see through clouds. And then most of these systems are available. The two on the bottom right-hand corner, the Bayesian system from Canada is not operational yet, and the disturbance index, they're hoping to put it in CEPL. They have the code is available, so if you're a Google Earth Engine savvy person, you can modify that or run it for your area. So that one is semi-operational, I would say. In terms of detection delay, just the difference between radar and optical, Johannes had a really great paper where he looked at 10 sites in the Amazon, and site 3 was a very cloudy site, and he plotted the delay, which is a triangle for site 3. It's a far shorter delay and when the alert is available than the two optical systems, is the square and the diamond. In contrast, he also looked at a large agricultural site where optical sensors are much faster because the radar has trouble distinguishing between the backscatter from trees on the ground versus standing trees. And I think with NISAR coming out, that will probably change, but that with Sentinel-1, that system has very short wavelength, and so it struggles with to distinguish debris on the ground from standing trees. Okay, so this is going to be the main part of the talk. I'm just going to go through what we learned, what we saw in these workshops, what we did, what we learned. So I'll show you what we saw on the ground and what the system saw from space and when they saw it. And I'm trying to compare them based on the area of detected tree loss as well as the timing of detected tree loss. And I was controlling for forest mass, the observation period, date we accessed system data, and I tried to look at high confidence alerts. So not just one observation that's different from historical values, like 2 or 3. Each system has their own definition of high confidence, but it's always more than one observation, oftentimes 3 or 3 out of 5, something like that. Many of the systems allow you to set parameters to choose those values. So this is the first one, Vietnam. It was a very small site. It was 1.4 hectares, and it's was being converted to an acacia plantation. And the site is within this red box. And again, here we see the red box over the summer months. In June, it's intact. July, it's thinning a little bit. August, it is deforested mostly. There's still some standing trees, it looks like. And by September, it's completely bulldozed and clear. So just a little bit on the methods, or I guess I'm getting ahead of myself. This is just an example of like one of the tools, like if you go online, they're often available with web browsers. You can play an animation of these alert pixels when they occur. You can also download the pixels, which is what I did, so I could compare them and tally up numbers in GIS. So the site for Vietnam is this red site that I always say looks a little like Italy. The pixels represent the color represents the day of forest loss detection. So and it's just day of the year. So 1 would be January 1st, December 31st would be 365. So I just numbered them. So the yellow ones are earlier. There's a lot of deforestation in this area that's not just at the field site we visited. the red ones are later, toward the end of the period. So in this case, October rather than January. So when I did this comparison, I pulled off the pixels, and the image on the left is what you saw on the previous page. The middle one is a forest mask that I got from Hai in Vietnam. Thank you, Hai. I don't know if you're listening. And then on the right, I clipped all of the pixels to the forest mask. So we're just looking at one section, which was primary forest. So this is this is one of the two key slides for Vietnam, and there'll be similar ones for the other sites. So essentially, I have the system side by side. I have to move the pictures of participants so I can see my full screen. So all of these systems capture the actual deforestation site, the small area, quite well. They're out of the 1.1 hectares in the forest mask, most of them are right around 1.1. JJ Fast is an exception because it's below their detection threshold. Because it's such a small site, I looked at a 1 kilometer square around it, and then within the forest mask, CNES and RAD and the disturbance index pick up more pixels in that 1 square kilometer than the other ones. And so here's the other key slide for Vietnam. The deforestation event, the actual clearing was around August 4th, as far as we could tell, based on planet data. And then I plotted the mean date of the deforestation alert pixels as a big dot here, and then I just drew a line to indicate the first and last dates of the my cat is walking in front of my screen. The first and last dates of the alert pixels. So in this one, we see Sepal picks it up quite early, just within a couple weeks. GLAD, Landsat, RAD, and DS are about a week later, and the CNES system is like a month later. I'm not sure why. It's just the way it was. So moving on to Paraguay, we didn't have as many systems here. The RAD sensor was offline, so Global Forest Watch collapsed into just GLAD. CNES is not in Paraguay because it's a French space agency system, and they focused on former French colonies. They intend to go pan-tropical, but as of now, that has not happened. So this site we looked at is Mabaracaiu near the Brazilian border. So looking big picture on the left, zooming in a little more on the right, and zooming in even more, we have a comparison just to give you an overview of what's happening in this area. In the last 10 years or so, it was quite intact. 2018, 2017, and then there's been a huge amount of deforestation, mostly for illegal crops, I believe. So zooming all the way into the site that we intended to visit but could not, or it looks a little bit like a pair of shorts, and you see the difference between the earlier image, 2016 to 2018, and then 2022, right after the deforestation event. So we had 5 systems here. GLAD Landsat picks it up. It doesn't get quite at 30-meter scale. It doesn't get quite the resolution and quite the area of some of the other systems. JJ Fast doesn't pick it up at all because it's below their detection threshold again. Sepal, both of Sepal, based on Planet and based on Landsat and Sentinel-2, do a really good job of capturing the area, as does the bulk system. In terms of the timing, the bulk system was very early. The deforestation occurred between these vertical green bars. Sepal is a little bit later, a week or two later, and Glad Landsat was quite a bit later, like another month or so later. And just, I made this slide just to indicate the timing, how the timing changes from the first anomalous pixel versus like a confirmed alert. If you're only looking for one pixel, the upper left, if you're only looking for one anomalous observation, these pixels show you the timing and they're much lighter in color. If you have to wait for 3 observations to confirm that something is going on, that the deforestation is real and not just a weird thing in the remote sensing data. You can see the pixels are much darker, indicating, in this case, about a 2 to 4 week delay to get that confirmation. So it takes time. If you want to be sure something's going on, it takes time. And then the bottom, that pair on the bottom are same sort of thing, first alerts versus confirmed alerts. But we were using planet data. We just took every third day. We're using daily data, but only going every third day. So it's a little more subtle shift, but it's still there. There's still going to be a delay. Guatemala, we have a 5-hectare site. It's all within the forest mass pretty much. I asked developers for pixels that were in a 25-hectare area, and then here's the comparison. Glad Landsat doesn't capture much. The Glad Lab came up with a new system that just before this workshop, it does a really good job of capturing the area. JJ doesn't capture as much area. And then Sepal, Rad, Bulk, and Diaz do a pretty good job of capturing the area. Rad is a little shifted, I think probably because it's very steep in this area, and radar struggles in steep areas like most remote sensing sensors. In terms of the timing, the Glad Landsat not only did it pick up very few pixels, but it was very late. The others were all mostly clustered together. JJ Fast was a little earlier. They got lucky because their sensor probably passed over just after the event, and their sensor revisit time is 42 days. So if it didn't get it right then, it would have been quite a bit further to the right. Diaz was a little bit later than the other ones. So the last site we looked at was Libreville, Gabon. 2023 on the left, 2024 on the right. It's about a 3.5-hectare site, and it was intact at the end of November, and then it's a very cloudy place. The first image we could see mid-December. It's hazy, but it appears to be deforested. And December 15th, you can see it even better. This is what it looks like on the ground. It's being cleared for banana and manioc. And then the key slide for area, Glad Landsat doesn't pick up much, but Dist Alert does a really good job. JJ Fast does okay. It's 50-meter cell resolution, so it's a little chunky looking. Rad does well. Most of the others do well. CNES, I think that it is outside their forest mass, I think because it was secondary forest. So I would expect CNES, because the algorithm is similar to RAD and they both use Sentinel-1. I would expect it to be similar to RAD, but it kind of highlights the importance of having an accurate forest mask or choosing a forest mask that works for your purposes. In terms of timing, Glad Landsat also very late. Most of the rest of them were about sort of picked it up late December. The timing of deforestation was between the green bars. So it was somewhere between late November and mid-December. We don't know exactly when because it was so cloudy, but it's at least a 2-week delay from the deforestation event to when most of the systems pick it up. After the fact, I compared sea trees, which was also quite late, and then the system from McGill was actually the latest in this case, and the developer doesn't know why. He is researching it. He was surprised by that, and it usually does better. But no, these systems don't always work the same way in different sites. This is just sea trees, but I won't talk about that. But they have a system that you can look at interactively online. So key takeaways. First, the different systems give different results depending on the site and the weather. Combining them makes sense. It will allow for earlier detection and higher confidence. Second, systems with multiple sensors are more robust. They can remain operational if one sensor goes on offline or it's a cloudy period and the optical sensors aren't providing much useful data. Third, there's a trade-off between receiving early alerts and building confidence. So if you want to avoid false alerts, it takes more time. Fourth, for technical users, SQL offers a lot of control of parameters. So you can choose whether you want early detection or false alerts. You can set those thresholds. So if you want a lot of control, SQL is a very good option. Next, forest mask is important, as we saw with the CNES system. Next, there are some new systems there being developed that identify drivers. Currently, most of these systems they just tell you when tree loss occurs. They don't tell you if it was from a typhoon or from logging or from fire. And lastly, for illegal activities, preventing deforestation, it may have more to do with the politics and the law enforcement because we are getting pretty good at detecting forest loss early. I think in plenty of time to get out there and do something if the social infrastructure is there. Lastly, these systems require a well-designed process. There's a lot of moving parts. You are acquiring alert data, combining alerts, possibly evaluating validity, prioritizing alerts because you have a lot of them oftentimes, notifying law enforcement and taking action. And I saw this slide at a presentation at Google for Good, and this was based on kind of old data and old GLAD system, but over a 5-year period, there were on average 170 alerts per day, and sometimes more than 1,000 per day. So it's not enough just to have a system. You have to have post-processing capacity and a plan for how to prioritize alerts and maybe thresholds, and like you only want to look at alerts above a certain size or in protected areas, for instance. But it takes some thought. And I think that's my last slide. So thanks for your attention, and I'm happy to answer questions. I don't know, Patricia, should I stop sharing my screen? I think we have
Yes,
questions
please.
for Sylvia and for me together.
Yes, thank you, Paul. Thank you for this great insights. So we don't have much time actually, but we will have now questions from the audience that they have already submitted in the registration form. Marcela, could
I'm looking for it, but I will please ask the people from the audience if they have questions. This is the time, and while I search for the ones we got from the registration.
yes, and just a reminder, we have the link from the tool for submit the questions during all the webinar, and actually it will be available after the webinar. If you don't have time now for questions, you can submit your questions later.
Yeah, we have a few questions in the
Thanks, Ashley.
chat. Yeah. We have one from Patricia. Have you conducted tests or do you plan to monitor and detect alerts for ecosystems other than rainforests, such as dry forests or Andean forests? This is a question for Paul. Yeah.
Yeah, I saw that question in the preview. It's a great question. Dry forest and also depending on your forest definition of forest, if it's like 10% cover, it's so much harder than a closed canopy forest. And I'm not a developer. I know almost all of the developers of the systems I showed, and um, I think if I had to guess, I think that the dist alert system would, assuming it's not super cloudy like Gabon all the time, or Guyana Shield, the dist alert system might work better in something like a dry forest because it's a land cover change system. So it works on grassland, cropland. I don't remember off the top of my head all the categories, but they essentially look at all different land covers. And so I think that the design of that one is more likely to capture a change in a very open forest or sparsely a forest with sparse trees. So that just off the top of my head, I think that would be the most helpful one. I think a lot of the other ones will be very challenged to capture changes that, if a pixel goes from 2 trees to 1 tree, for instance, it's perhaps not a big enough change to register.
Thanks, Paul. We have another question in the chat from Sunil about just regarding the use of multi-source data for forest disturbance change detection. For example, using different satellite sensors where selective felling or specific trees are quite often.
So I didn't follow. What was the question?
Yeah, the question is about the use of multi-source data for forest disturbance change detection. I'm not sure, Sunil, if you wanted to ask the question, you're welcome to come off mute.
Yeah, having multiple sensors is, I think, definitely an advantage and makes the systems more robust. For instance, if you have a cloudy period, the optical sensors won't give you much data, but you can use radar. And also like in Paraguay, the Sentinel-1 was offline, so we were able to use optical. So having more sensors is always an advantage. It will always give you, your alert will always be at least as fast as the best system. So I think there aren't really disadvantages to having multiple sensors.
Great. Thanks, Paul. Appreciate it. If you have any additional questions, feel free to add them into the chat or the Padlet board. I'll send the link and we can send responses. You'll have access to that after the webinar. Thank you.
Yes,
Thanks,
Ashley. Thanks, Paul, for your presentation. Let's move to our second session, where we have Crystal Wispet from C Group. She will talk about the ongoing global initiative, historical burn mapping and burn probability assessment using random forest. I'm pleased to introduce Crystal. Crystal is a forest monitoring specialist at the Special Informatic Groups. She has been working as a key contributor to the Zero Carbon Program's work on fire prediction and mapping tools and have involved in piloting these methodologies in collaboration with national partners in Nepal, Ghana, and other countries. Crystal, please go ahead.
Okay, I'm going to take over the screen sharing. Okay, so again, my name is Crystal Wespestad. I'll be speaking on the ongoing global initiative. So this is ongoing work where we're working on historical burn mapping, and most importantly, how it leads to burn probability assessments using a random forest model. So first, let's talk about why this type of work is necessary. There is a current gap where many regions are experiencing new or rapidly changing fire risk because of climate change and changing fire regimes. Current risk assessment methods are often region-specific and limited to the areas that already have well-documented fire histories. So these methods can be difficult to apply in other contexts. That is mostly because fire regimes and drivers vary widely across the world. There are a lot of common human drivers, but the patterns are specific to the area, and the different timing of fire across the world is another factor. So we have an opportunity to try and solve a piece of the fire risk puzzle. We want to specifically work on the probability of burns because we think that this can be addressed in a more universally applicable manner using machine learning and remote sensing. So in this diagram here, you can see that burn probability is just one piece of the overall problem of fire risk, which also includes vulnerability and the difficulty of suppression. So we're asking, how do we use this information to manage fires? That is our end goal. So this project started with a series of small grants offered by Google, where they were trying to get others to test their embeddings data set for different purposes. I'll talk a bit more about the satellite alpha Earth embeddings a bit later if you have not heard of them. But we proposed to do projects where we develop a globally transferable method for mapping wildfire risk using AI and satellite embeddings as the data set. This is a collaboration between the Surveyor Network, the AI Collaborative Wildfire Network, and several others. There is some of the countries are being supported by Spatial Informatics Group or Silvicarbon. So here's an overview of the whole project. Again, we start with the need that wildfire is increasing. We have this new data set, the Alpha Earth embeddings, which was promoted via the small grants. There's a collaborative effort started by all of these groups, and all of those groups brought in representatives from different countries where we could test our approach in several different areas. We have countries joining from South America, Africa, and Asia. And our approach is to adapt a previously used method, but to make it more universally applicable. So I'm going to be referring to a method that was published by one of my colleagues for fire probability mapping in Thailand. Our method builds upon this work, but we're trying to make it more generalized and test it across many different regimes and countries through a collaborative approach. Here is that paper, the burn probability mapping in Thailand using machine learning, notably random forest. This paper demonstrates the use of empirical quantitative modeling to link real environmental and human conditions before each fire season to the likelihood of fire occurrence. By identifying where fires are most likely to occur, the end goal is that managers can prioritize prevention, resource allocation, and community preparedness before the next fire season begins. So let's back up and explain the methodology of the Thailand paper a bit more. So in this example, we know the main environmental and socioeconomic drivers of fire in Thailand. On the left is representing all the different data sets that represent those environmental and socioeconomic drivers, such as topography, precipitation amount, distance to roads where people could access regions that they might burn, and some socioeconomic maps as well. When combining that with this excellent data set that Thailand has of their historical fire occurrences, so they are lucky enough to have hand-drawn locations of where burns occurred in several years, I think 10 years at least back. And that really rich data set combined with these environmental factors allowed them to train a machine learning model. So when you distribute points in the locations of the historical fires, both inside and outside the fires, you can extract the information of all of these variables, environmental and socioeconomic predictors, and say, at these locations, these conditions are likely to cause fire or be related to fire, and these conditions are more likely associated with non-burned areas. So once you give enough of those examples to the machine learning model, it can then predict where fires might occur in a new year. So once it's learned the fire examples and variables that led to those fires for the previous 10 years, if I give it the same variables for 2025, it can say where are fires most likely to occur in 2025. And that's the final map that it makes on the right, a burn probability from 0 to 100 of where fires are expected. So we want to be able to take that method and adapt it so it's more universal. We need to deal with the fact that human influences on wildfire ignition are highly context dependent, and the data sets are different across the world. The environmental predictor data sets differ in spatial resolution, temporal frequency, and continuity. And finally, the fire occurrence records vary in availability and consistency. Thailand had that amazing example of the 10 years of hand-drawn fires, but that is not common across the world. So in the Thailand work, 42 different variables were fed into the model and were tested, but some of those are only available locally in Southeast Asia. So we're seeking to test whether this new data set, the Alpha Earth satellite embeddings, can potentially replace all of those individual and sometimes local data sets. And with that replacement, maybe we can simplify the process significantly, reducing the number of input variables and reducing the necessary data preparation. So if you haven't heard of the satellite embeddings, they are annual data sets. It acts almost like a virtual satellite constellation. They are analysis ready for training machine learning models. They're referred to as an embedding vector, and they have 64 different vectors representing the qualities of each pixel. So you can kind of think of it like Landsat imagery has 4 different bands, red, green, blue, and near infrared. But this one has 64 different pieces of information. So it's a really rich data set at each pixel. And that is because it's generated from many, many different satellites all together. This is showing that it was trained on imagery from Sentinel-2, Landsat, ALOS, Pulsar, Copernicus, DEM, JEDI, GRACE, all of these data sets wrapped into this one amazing vector-based embeddings. And that, again, was the point of the original grants, was to test a method using this new data set. But there's another piece. The historical fires that were available in Thailand, we need to be able to replace that with something that can be done everywhere. So not all countries have access to this hand-digitized data set that takes a whole lot of time. but we need to create that in a different way. So our method needs to be at least partially automated so that the approach can be used when human resources are limited as well. We don't want to say that everyone has to hand digitize their burns in order to use our method. So in order to recreate those historical burns, we tested 2 different approaches. We wanted to see if one of them worked better and could be used everywhere, or if we needed to combine them in some way. So first we tested what I'll call the aggregated DNBR mapping approach. So DNBR, or just, you've probably heard of NBR, the normalized burn ratio. DNBR is the difference normalized burn ratio, which calculates the DNBR for comparing the spectral response before and after a fire. You can see the change in the NBR value. So we do that in an aggregated manner where we run that same analysis for several image pairs in a row. So like look a couple weeks apart and then run it again and then run it again and then run it again. So for a several month burn season period, you'll see all of the results from, I think actually I'll jump ahead 1 slide to show you the DNBR values. And for each of those 2-week periods all together, we select wherever the 0.27 value or higher is present. And we say, okay, if at least this threshold has been met, we consider that a burn occurred, and we'll count that as a yes burned in our burn season. So that's how we're making our binary burn, no burn map in an automated way. Then we tested the bulk D method. This is one that Paul discussed in his talk. This was developed at McGill University in Canada at the Cardiel lab, and it can be run specifically on the NBR index to look for changes most likely associated with fire. So bulk D stands for Bayesian updating of land cover deviation. So it uses Bayesian logic to test every single pixel for whether the index value NBR has meaningfully decreased, increased, or stayed the same over a given time period. And we're looking for where it's at least 50% probability of NBR decrease, which is an indicator of a burn occurrence. Okay, and then here's just another example of that the bulk D algorithm. So you'll see in this graph, the NBR was high typically, and then at some point it dropped down and you see these lower NBR values. So it's looking for where NBR is changed from where it typically is. And then this red, green, blue graph is showing, let's look at the red line, the likelihood or the probability that NBR is decreasing from image to image is low, low, low. And then in mid-August, the probability that a change occurred spikes way up, and you'll see that we are now fairly confident that NBR has decreased within our time period. This is a nice graphic showing the NBR on the left and the result of the bulk D algorithm on the right. So you'll see this burn show up in white on the left side, and then very quickly it becomes highly confident that NBR has decreased, and that would be our final bulk D result of historical burns. So we asked all of the people participating in the study to test both of these algorithms and then compare them to other known data sets of fire, such as the GABAM dataset, which has a good map of fires in 2021. There's also the MODIS and VEERS maps of where fires have occurred. And that is done via a Google Earth Engine GUI, which you're seeing in these videos. And that was tested by everyone in the study. Yes, okay. So this is an example of one of those tests that was done in Brazil. We observed that the NBR algorithm, in this case, was picking up things that probably weren't fire, they were actually changes in agriculture. And these are the blue circles you're seeing here. So that was some of Brazil's results of their testing. In Peru, in red, you'll see the bulk D algorithm result. And in blue, it's a locally available map that was hand digitized of burns. So they have fairly confident in that one. And you'll see that there is some discrepancy between the hand digitized burns and the bulk D results. I think bulk D was actually over detecting change in this case. And then we compared where both algorithms were finding change within the different land cover types. So in Kenya, they found that DNBR was finding more change in general, almost 2,000 hectares compared to the bulk D algorithm finding 1,000 hectares, and they only agreed or where those fires happened for 950 hectares. And that varied by type. You'll see there's more disagreement where NBR is detecting more change, especially in the regions of trees and shrubland. So overall, after all of that testing of historical burn mapping, we decided that neither approach was perfect and the map results could not be used blindly as a true model of where burns and no burns occurred. We could not just directly give those results to a machine learning algorithm to learn from. However, they are an excellent start. They are giving us a starting point to find likely areas of burn or no burn that we can sample. And as Paul said, using both algorithms together may actually have a lot of advantages because one might perform better in certain environments than the other or on specific types of fires as well. So we opted to do a sampling approach where we use both algorithms. And we divided our regions into two strata. Strata 1 is areas we are fairly confident there were no burns because neither DNBR nor bulk D detected a burn there. And in strata 2, we allowed those to include areas where both bulk D and DNBR or just one of them detected a burn. So DNBR and or bulk indicated a burn. We then use proportional sampling. Unless the area is really, really small, such as a really tiny area was burned, then we required at least 50 points, sample points to be in those regions, just so we can get enough examples of what might lead to a fire for our training algorithm. These samples must be collected from multiple burn seasons as well. So we created a DNBR and a bulk D map for 10 years in a row, and then did this stratification for each of those 10 years. And finally, at least 500 meters must be the minimum spacing between the sample points because we wanted to force the sampling to find not just the really large fires, but also the small fires that might have been skipped. Now, as I said, we cannot 100% trust those algorithms as a map is being true. We know there is bias in the map. So we are now at the stage of where we have created samples in those two strata, and we want to double check them using the CEO Collect Earth Online algorithm. We will verify those samples as yes, they are indeed a burn or not a burn, because we want to give our random forest algorithm good examples. The model can only be as good as the data it was trained on. We know, however, that resources can be limited for spending the time on collecting this information. So we added these labels to the points where we gave a little hint as to why we might be high in confidence on that point or have low confidence and really want to double check them, such as both bulk D and DNBR said there was a burn, or maybe only one of them. So if only one of them said yes, maybe I really want to focus on checking that point. We also overlaid them with NASA firms data to see, and you'll see that in this map. And that would be another indicator of higher confidence that a burn did happen. On the right, you're just seeing recording of some of the tools inside Collect Earth Online. where it can give you a graph of indicators like NDFI or NDVI, where you'll see a drop that most likely means a change did happen. And you can double check that within CEO to verify the accuracy of that sampling point. Then I'm going to quickly go over some case studies of 2 countries that are participating in the program. First, Ghana. These slides were prepared by Foster Mensa. In Ghana, fire is a recurring national hazard. The peak fire season is between November to March, and most fires are human caused for agricultural purposes, charcoal production, hunting, etc. And they are causing issues with risks to biodiversity, agricultural lands, and rural livelihoods. When Foster did the testing in Ghana, he was comparing bulk D and DNBR. These are his results for that. His preliminary results said that DNBR had a greater spatial agreement with the Gaban data set. That is another map of burns that's fairly well trusted. It delineates larger and more continuous burn perimeters, but it may overestimate burn extent. And then bulk D produces more conservative burn delineation, but they are sensitive to probability threshold selection. In this image on the right, we used 70% probability. In the end, we opted to reduce that down to at least 50% certain. All right, and this just highlights the importance of an independent reference data to verify these or using these 2 algorithms together. So how are they going to use the results in the end? In Ghana, they will be using it for wildfire risk assessment, developing seasonal burn probabilities, identifying recurrent fire hotspots, and using it for decision support, protecting forest reserves, etc. And then in Nepal, these slides were created by Rajaram and Sudeep Raham. So in Nepal, fire is becoming an issue because of the fuel loads being increased. And these trends of not cutting down forests have really caused elevated fire risk, and they don't have an operational risk system to guide their planning. They do have this really excellent forest fire monitoring system, but only looks backwards as to where the fires are happening recently or back in history. And during their testing, Nepal found that bulk D detected larger change areas than DNBR. The bulk DNBR overlap was only moderate. And they did also observe an issue with the use of Dynamic World's water mask in their region, where it did not work in the higher elevations for certain years. So we updated our tools so that it would work using a local water mask, and they have rerun the results using that approach. The potential benefits for Nepal is they will explore informing effective forest management, targeting mitigation efforts in areas most likely to have burns in the future. It will help them with their RED+ monitoring. It will improve their current monitoring system to not just look backwards, but also forwards, and will increase their local capacity to use machine learning tools and these new data sets. So this is my last slide. I just want to say where we are now and conclude that we are currently at the sample verification stage, and we will soon be ready to train the random forest model on these verified points using the alpha earth embeddings as the training imagery. This work will ultimately be published, and the methodology will be made publicly available. All participating countries will be able to use the results for their own purposes, such as for fire risk management or resource allocation. And we're looking forward to all the actions using this burn probability result around the world. That's it for me. Thank you.
Thank you, Crystal, for your presentation. Now we will pass to the Q&A session. I think Ashley will read some questions for you.
Yeah, thank you, Crystal. We have some questions from Sunil in the chat, and And if there's others, please feel free to add them to the Padlet board. We can answer them after the session is over. Sunil was asking questions about sort of parameters for assessing risks and adding response time to a fire event as a parameter for assessing risk. Also, different association, adding in different independent variables such as topography, socioeconomic predictors. Yes, these were some of his questions in the chat.
Okay. For a large country like India, there are different socioeconomic, topographical, and environmental parameters across the country. Yes, yeah, that's true. Can we have some prior probabilities for pixels under higher severity burnt class? So that's an interesting idea. I think you could. What we're developing right now is supposed to be more generalized so that it just works pretty well everywhere, but you could add in additional parameters or new variables on top of the embeddings if there was something locally that you really wanted to push for, as this is an indicator of fire here. So right now we're focusing on just using the embeddings, but then the idea is in local areas you might be able to add on a couple more. Can response time to a fire event be a parameter assessing the risk? Yes, that is for the fire risk. We're focusing on burn probability only, but the final risk is about exposure and vulnerability and response time, as you said. And then lastly, I think we can have some comparison of random forest-based burnt areas assessment with the result of other machine learning classifiers. There could be spectral mixing of signatures in a large segment of fire affecting areas which needs to be unmixed with higher precision. Okay, yeah, so other machine learning algorithms may ultimately be better for burn probability mapping locally, but we were choosing to use one that was lower cost for collecting data and easier to understand so that it could be used quickly by a larger set of people. But something like a convolutional neural network requires a lot of data collection and a lot of tuning. So you can do that locally, but we are focusing on a simplified general approach. I think that's all of those questions.
Yeah, thank you, Crystal. Those are the questions we have. And we have to wrap up now. So I'll hand it to Patricia.
Yes. Yes, thank you, Crystal, for answering those questions. Yes, as Ashley said, we got out of time. But I want to first thanks for all the presenters from today. Thanks Sylvia, Paul, and Crystal for your great presentations. In behalf of all the institutions that are organized this webinar series, many thanks for you. And as closing, we want to remind this session has been recorded. This time we will share both recording from the blog 1 and the blog 2 and the presentation materials. So I have one last announcement that we will have our third and final blog of this series. It will be very soon, so stay tuned for the announcement. And I want to thanks for joining us today. We hope to see you again in blog 3 and have a great rest of the day. Thank you very much.